All right, we're moving into part 3 of 10.7. This is turning out way longer than I wanted it to, but I think the more examples we see, the better. So hopefully this will be a little bit shorter. I have one more example to go through, and then just a couple of really important theorems before we get to the last section that we need to focus on, section 8. So let's just do one more quick example of finding the interval and radius of convergence of these power series. So this example, we're going to do the infinite sum. It's still going from n equals 0 to infinity, but now we're going to do x to the n divided by n factorial. So we want to know where does this power series converge. This power series, just to write out a few terms so you can see what it looks like, you have 1 plus x squared divided by 2 factorial. Remember, 2 factorial is just 2 times 1, so it would just be a 2, plus x cubed over 3 factorial. 3 factorial would be 3 times 2 times 1, so that would be 6 down there, and that would just keep going forever and ever and ever. Okay, it's going to be the same questions as before. Find the interval of convergence and the radius of convergence, or cover range, as I spell it. Okay, remember to do this ratio test. I'm going to make this ratio test look a little bit cleaner. I'm probably going to skip a little bit of steps here. Remember what the ratio test, wow, it's been a long day. With the ratio test, you're taking that absolute value. So it's the absolute value of the n plus 1 term. So just to write that out, that'd be x to the n plus 1 divided by n plus 1 factorial. All right, so it's going to be that thing divided by, and then now we're going to have the nth term, x to the n divided by n factorial. All right. Remember, we're just going to rewrite this as the top fraction multiplied by the reciprocal of the bottom fraction. So I'll go ahead and write that all out. You still have the absolute value. This is still going to be x to the n plus 1 divided by that n plus 1 factorial. But now it's going to be multiplied by the reciprocal of the bottom, n factorial divided by x to the n. All right. We're going to use the same trick as the last example. This x to the n plus 1, I'm going to write as x to the n times x. My n plus 1 factorial, we've seen this before, but I'm going to write this as n plus 1 times n factorial. And as I write it out, I'll explain it a little bit. So just to write out what we're doing, my numerator is going to be an x to the n times an x. My denominator, I'm going to write as n plus 1 times n factorial. All right, so just to explain this again, this is just the first fraction. X to the n plus 1, we're going to use the product rule for exponents and write that as x to the n and then x to the 1. That's what we have here, x to the n times x to the 1. N plus 1 factorial would be n plus 1 times the next number down n times the next number down times the next number down. Or we could just rewrite this as n plus 1 factorial as n plus 1 times the next number down factorial. My other fraction I'm just going to leave alone. I'll just leave that as n factorial divided by x to the n. And then you should see a lot of stuff cancel out here. So I have an x to the n on top and an x to the n on bottom. These two things just cancel out. And then we have the n factorial top and bottom that cancel out as well. So x to the n cancel, n factorial cancel. And then we're left with, we still have the absolute value because we don't know if this x is positive or negative. We have to keep the absolute value going the whole time. We're just going to end up with an x on top and then an n plus 1 in the bottom. Okay. Don't forget that we're supposed to be taking the limit as n goes to infinity of all of this stuff. As n goes to infinity of this, x is just a number. That stays what it is, but my n in the denominator blows up to infinity. So I hope you can see that this whole thing just goes to 0. And remember that the ratio test gives me my p-value. So here my p is always 0 regardless of the x. And because that p-value is less than 1, remember that that says that my series converges absolutely. And because I don't have an interval here, that means that it converges everywhere. So since p is less than 1, regardless of x, this says the power series that we started with up here, this thing, converges absolutely on entire number lines. Another way of thinking about that is that R value is infinity. So the radius of convergence is infinity, or you can think of it as that the interval of convergence is going to be the entire number line, so from negative infinity to positive infinity. And that's it. So that's all there's going to be for this example. This would be a power series that converges for all x, not just in an interval. So if you figured out what this thing actually converges to, which by the way we do not know what this converges to, but if you figured out what this converges to and you graphed that function and then this infinite series, it wouldn't just approach it on just a small interval of values. The entire graph would actually approach each other. So it's pretty nice. Okay. So the only other things that I wanted to point out here in this section 7 is just three more theorems. So let's write those out. The first theorem is if you know that you have this that you have this power series that converges. So this is just a generic one. So when you have a to the n, x to the n, this power series you know converges absolutely. So this one, we'll just say that it converges where x is less than that radius of convergence r. This thing is centered at 0. Then you also get another power series that you know converges. This would be the power series with a to the n's out in front and then x to the n inside of some function. This also would converge absolutely for any continuous function f. But we have to change my interval around a little bit. This would only converge on the interval f of x is less than r. All right. So what this allows us to do, just to kind of give you a quick little example here, is that if you somehow find a power series that converges absolutely, then you can apply functions to it, or vice versa. If you have something that has a function applied to it, you could go backwards. So just to kind of to show you what I mean, if you had a power series where you had your constants out in front, but these weren't just x to the n's, let's say it was something like the natural log of x to the n. If x to the n converges as a power series, then you automatically get that the natural log of x to the n converges as a power series, but not on the entire interval. Only natural log of x is less than r on that interval instead. All right, so just a key little thing that you can do. If you have a power series, you can apply every single one of those power functions to another function on the outside. Okay, some other theorems that are really important is this one. Again, if you have some power series, this one we won't have converge at 0. This one will have be centered at a. So if you have a power series that is centered at a, and let's say this has convergence of radius, where my radius of convergence is just some positive number, then it defines a function. All right, so I'm being kind of nonchalant about this, but this is super important. Basically what this is saying is that if you have a power series that converges, then you can just treat the power series as its own function f of x. Okay. And not only can you treat it as a function, but if you are treating it as a function, this function has derivatives. And if we look at those derivatives, so let's say f prime of x, we don't have to do any work because our power series does it for us. Instead of taking the derivative of some unknown function, we can just take the derivative of the power series term by term. So if I take the derivative of this, remember we're taking the derivative with respect to x, this is going to be a chain rule here. So we're going to bring our n down, still have that c to the n out in front, and that's going to be x minus a to the n minus 1 power. This generates a new power series that would also converge, and it converges on the same interval. And we can keep taking derivatives and keep taking derivatives over and over and over again by just bringing down more powers of n minus 1. This is going to be very important here in the next section. So when we get to that, I'll refer back to this theorem. Not only can you take derivatives of these power series, Also, you can take integrals of functions defined by power series. And it's nothing too crazy. All this is saying is that if you do have, or if you want to take the integral of a function, what you can do instead is that you can just integrate over the power series. So if f of x is defined here, c sub n x minus a sub n, I can just take the antiderivative of that. Antiderivative of that is we're going to raise that power to n plus 1, and then I have to divide by that n plus 1. So we're going to do 1 over n plus 1 out in front. We still have that constant c sub n, but now it's going to be x minus a to the n plus 1 power. You are going to have to worry about the plus c though, so just know that there should be a constant for the antiderivative out in front. The point though is that if you have a function defined as a power series, you can anti-differentiate the function by anti-differentiating the terms of the power series instead. And remember that usually the function is very complicated, but this is just a polynomial. It is easy to take derivatives and anti-derivatives of polynomials, which makes power series so nice.